Hello and welcome to the session on History of Mathematics and Egyptian Civilization. The rise of civilizations characterized by the use of metals took place at first in the river valleys such as those in Egypt, Mesopotamia, India and China. Hence, we shall refer to the earlier portion of the historical period as the Potamic stage. The chronological records of the civilizations in the valleys of the Indus and Yangtze rivers are quite unreliable, but fairly dependable information is available about the peoples living along the Nile and in the fertile crescent of the Tigris and Euphrates rivers. Before the end of the 4th millennium BC, a primitive form of writing was in use in both the Mesopotamian and Nile valleys. By the Napoleonic expedition in 1799, a trilingual stone with 3 different languages had been discovered at Rosetta. This large tablet found at Rosetta, an ancient harbour near Alexandria, contained a message in 3 scripts: Greek, Demotic and Hieroglyphic. Knowing Greek, Champollion in France and Thomas Young in England made rapid progress in deciphering the Egyptian hieroglyphics, that is, sacred carvings. Inscriptions on tombs and monuments in Egypt now could be read, although such ceremonial documents are not the best source of information concerning mathematical ideas. Egyptian hieroglyphic numeration was easily disclosed. By the use of a simple iterative scheme and of distinctive symbols for each of the first half dozen powers of 10, numbers over 1,000,000 were carved on stone, wood and other materials. A single vertical stroke represented a unit. An inverted wicket or heel bone was used for 10. A snare somewhat resembling a capital letter C stood for 100, a lotus flower for 1000, a bent finger for 10,000, a barbet fish resembling a polyvogue for 1 lakh and a kneeling figure, perhaps god of the unending, for 10 lakhs. Sometimes the smaller digits were placed on the left and sometimes the digits were arranged vertically. The symbols themselves occasionally were reversed in orientation so that the snare might be convex toward either the right or the left. The Egyptians early had become interested in astronomy and had observed that the annual flooding of the Nile took place shortly after Sirius, the dog star, rose in the east just before the sun. By noticing that these heliacal risings of Sirius, the harbinger of the flood, were separated by 365 days, the Egyptians established a good solar calendar made up of 12 months of 30 days each and 5 extra feast days. But this civil year was too short by a quarter of a day. Hence, the seasons advanced about 1 day every 4 years until, after a cycle of about 1460 years, the seasons again were in tune with the calendar. There is a limit to an extent of mathematical information that can be inferred from the tombstones and calendars, and our picture of Egyptian contributions would be sketchy in the extreme if we had to depend on ceremonial and astronomical material only. Mathematics is far more than counting and measuring, the aspects generally featured in hieroglyphic inscriptions. Fortunately, the other sources of information are a number of Egyptian papyri. The most extensive one of a mathematical nature is a papyrus roll about 1 foot high and some 18 foot long, which now is in the British Museum. It often is known as the Rin papyrus or Arms papyrus in honor of the scribe by whose hand it had been copied in about 1650 BC. The numerals and other material in the Rin papyrus are not written in the hieroglyphic forms described above, but in a more cursive script. better adapted to the use of pen and ink on prepared papyrus leaves and known as hieratic. Numeration remains decimal, but the tedious repetitive principle of hieroglyphic numeration has been replaced by the introduction of ciphers or special signs to represent digits and multiples of powers of 10. 4, for example, usually is no longer represented by 4 vertical strokes, but by a horizontal bar, and 7 is not written as 7 strokes, but as a single cipher resembling a sickle. The principle of cipherization, introduced by the Egyptians some 4000 years ago and used in the Rin papyrus, represented an important contribution to numeration, and it is one of the factors that makes our own system in use today the effective instrument that it is. Men of the Stone Age had no use for fractions, but with the advent of more advanced cultures during the Bronze Age, the need for the fraction concept and for fractional notations seems to have arisen. Egyptian hieroglyphic inscriptions have a special notation for unit fraction, that is, fractions with unit numerators. The reciprocal of any integer was indicated simply by placing over the notation for the integer an elongated oval sign. The fraction 1 by 100 thus appeared like this. In the hieratic notation appearing in papyri, the elongated oval is replaced by a dot, which is placed over the cipher for the corresponding integer or over the right hand cipher in the case of the reciprocal of a multi-digit number. In the Arms papyrus, for example, the fraction 1 by 8 appears as like this. Such unit fractions were freely handled in Arms day, but the general fraction seems to have been an enigma to the Egyptians. They felt comfortable with the fraction 2 by 3, for which they had a special hieratic sign like this. Occasionally, they used special signs for fractions of the form n divided by n plus 1, the complements of the unit fractions. To the fraction 2 by 3, the Egyptians assigned a special role in arithmetical processes, so that in finding 1/3 of a number, they first found 2/3 of it and subsequently took half of the result. They knew and used the fact that 2/3 of the unit fraction 1 by p is the sum of the two unit fractions 1 by 2p and 1 by 6p. They were also aware that double the unit fraction 1 by 2p is the unit fraction 1 by p. Egyptians regarded the general proper rational fraction of the form m divided by n not as an elementary thing, but as part of an uncompleted process, where today we think of 3 by 5 as a single irreducible fraction. Egyptian scribes thought of it as reducible to the sum of the three unit fractions 1 by 3, 1 by 5 and 1 by 15. To facilitate the reduction of mixed proper fractions to the sum of unit fractions, the Rin papyrus opens with a table expressing 2 by n as a sum of unit fractions for all odd values of n from 5 to 101. 2 by 5 is equal to 1 by 3 plus 1 by 15. 2 by 11 is equal to 1 by 6 plus 1 by 66. 2 by 15 is equal to 1 by 10 plus 1 by 30. The last item in the table decomposes 2 divided by 101 into 1 divided by 101, 1 by 202, 1 by 303 and 1 by 606. It is not clear why one form of decomposition was preferred to another of the indefinitely many that are possible. At one time, it was suggested that some of the items in the 2 by n table were found by using the equivalent of the formula 2 by pq is equal to 1 divided by p into p plus q by 2 plus 1 divided by q into p plus q by 2. This indicates that the Egyptians had some appreciation of general rules and methods above and beyond the specific case at hand. And this represents an important step in the development of mathematics. The 2 by n table in the Arms papyrus is followed by a short n by 10 table for n from 1 to 9. The fractions again being expressed in terms of the favorites, unit fractions and the fraction 2 by 3. For example, 9 by 10 is broken into 1 by 30, 1 by 5 and 2 by 3. Arms had begun the work with the assurance that it would provide a complete and thorough study of all things and the knowledge of all secrets, and therefore the main portion of the material following the 2 by n and n by 10 tables consists of 84 widely assorted problems. Egyptian arithmetic operations. The fundamental arithmetic operation in Egypt was addition, and our operations of multiplication and division were performed in Arms day through successive doubling or duplication. Our own word multiplication is in fact suggestive of the Egyptian process. A multiplication of say 69 by 19 would be performed by adding 69 to itself to obtain 138, then adding this to itself to reach 276, applying duplication again to get 552 and once more to obtain 1104, which is of course 16 times 69. Inasmuch as 19 is equal to 16 plus 2 plus 1, the result of multiplying 69 by 19 is 1104 plus 138 plus 69, that is 1311. Occasionally, a multiplication by 10 also was used, for this was a natural concomitant of the decimal hieroglyphic notation. Multiplication of combinations of unit fractions was also a part of Egyptian arithmetic. Problem 13 in the Arms papyrus, for example, asks for the product of 1 by 16 plus 1 by 112 and 1 plus 1 by 2 plus 1 by 4. The result is correctly found to be 1 by 8. For division, the duplication process is reversed and the divisor is successively doubled instead of the multiplicand. The Egyptian problems so far described are best classified as arithmetic, but there are others that fall into a class to which the term algebraic is appropriately applied. They require the equivalent of solutions of linear equations of the form x plus ax equal to b or x plus ax plus bx equal to c, where a, b and c are known and x is unknown. The unknown is referred to as AHA or heap. The problem 24 in the Arms papyrus, for instance, calls for the value of heap if heap and a seventh of heap is 19. The solution given by Arms is not that of modern textbooks, but is characteristic of a procedure now known as the method of false position or the rule of false. A specific value, most likely a false one, is assumed for heap, and the operations indicated on the left hand side of the equality sign are performed on this assumed number. The result of these operations then is compared with the result desired, and by the use of propositions the correct answer is found. Many of the AHA calculations in the Rim papyrus are of a practical nature. In some places it seems to have had puzzles or mathematical recreations in mind. Thus, problem 79 dealing with a problem perhaps quite well known, in which in each of 7 houses there are 7 cats, each of which eats 7 mice, each of which would have eaten 7 ears of grain, each of which would have produced 7 measures of grain. The problem evidently called not for the practical answer, which would be the number of measures of grain that was saved, but for the impractical sum of the numbers of houses, cats, mice, ears of spelt and measures of grain. This bit of fun in the Arms papyrus seems to be a forerunner of our familiar nursery rhyme. As I was going to St. Ives, I met a man with 7 wives. Every wife had 7 sacks. Every sack had 7 cats. every cat had 7 kids. Kids, cats, sacks and wives, how many were going to the St. Ives? The Greek historian Herodotus tells us that the obliteration of boundaries 7 in the overflow of the Nile emphasized the need for surveyors. Problem 51 of arms shows that the area of an isosceles triangle was found by taking half of what we would call the base and multiplying this by the altitude. Arms justified the method of finding the area by suggesting that the isosceles triangle can be thought of as two right triangles, one of which can be shifted in position, so that together two triangles form a rectangle. The isosceles trapezoid is similarly handled in problem 52, in which the larger base of a trapezoid is 6. The smaller base is 4 and the distance between them is 20. Taking half the sum of the bases so as to make a rectangle, Arms multiplied this by 20 to find the area. In transformations such as these, in which isosceles triangles and trapezoids are converted into rectangles, we see the beginnings of a theory of congruence and of the idea of proof in geometry. The Egyptian rule for finding the area of a circle has long been regarded as one of the outstanding achievements of the time. In problem 50 of Arms, the area of a circular field with a diameter of 9 units is the same as the area of a square with a side of 8 units. If we compare this assumption with a modern formula, A is equal to pi into R, we find the Egyptian rule to be equivalent to giving pi a value commendably close approximation. No theorem or normal proof is known in Egyptian mathematics, but some of the geometric comparisons made in the Nile Valley, such as those on the perimeters and areas of circles and squares, are the first exact statements in history concerning curvy linear figures. In the construction of pyramids, it had been essential to maintain a uniform slope for the faces, and this concern led them to introduce a concept equivalent to the cotangent of an angle. There are other sources for the information about Egyptian mathematics, such as Cahun papyrus, Berlin papyrus, and an important papyrus known as the Golanishev or Moscow papyrus. Moscow papyrus contains 25 examples, mostly from practical life and not differing greatly from those of Arms, except for 2 that have special significance. Associated with problem 14 in the Moscow papyrus is a figure that looks like an isosceles trapezoid, but the calculations associated with it indicate that a frustum of a square pyramid is intended. Above and below the figure are signs for 2 and 4 respectively, and within the figure are the hieratic symbols for 6 and 56. The directions alongside make it clear that the problem calls for the volume of a frustum of a square pyramid 6 units high if the edges of the upper and lower bases are 2 and 4 units respectively. It directs one to square the numbers 2 and 4 and to add to the sum of these squares the product of 2 and 4, the result being 28. This result is then multiplied by a third of 6, that is 56. That is, the volume of the frustum has been calculated in accordance with the modern formula V is equal to H into A plus A into H plus H into H whole divided by 3, where H is the altitude and A and B are the sides of the square bases. Nowhere is this formula written out, but in substance it evidently was known to the Egyptians. If one takes B is equal to 0, the formula reduces to the familiar formula 1/3 the base times the altitude for the volume of a pyramid. How these results were arrived at by the Egyptians is not known. Let us summarize the major ideas in this session. This content helps a reader to visualize the growth of mathematics through Egyptian civilization. the practical application of mathematics, like the development of a calendar from the experience of flood in their land for the construction of pyramid, etc., shows that mathematics developed through the experience of their day-to-day life. The informations that they had are preserved in specially prepared papyrus leaves are the authentic references for us about the Egyptian mathematics. Now, you can try to answer the given questions here. First one, name the two types of notations used to indicate the numerals by the Egyptians. Second one, do you agree that Egyptians were interested in astronomy and they developed a calendar? And the third one, what do you regard as the chief contributions of Egypt to the development of mathematics? Explain why you regard them as important. Now, you can go through these books for reference. First one, Carl B. Boyer, A History of Mathematics, John Wiley and Sons. Florian Cajori, A History of Mathematics, Macmillan and Company. The third one, Parker R.A., The Calendars of Ancient Egypt, University of Chicago Press. Thank you for watching this program. Hope that you have enjoyed this session. We can meet again with another topic. Till then, take care.